starting the second session today. And this session, if you see, its number is your 7th lecture is coming up. Now it's already ready. We have with us Dr. Aparajita Ojha, who is a very senior professor from IIIT Jabalpur. And I know her around for last 3-4 years. We are discussing about the projects, and she has really supported when we have conducted in-campus machine learning, deep learning program in 2019. She was there with us in IIRS Dehradun. And I can really see it was really motivated to me. Such a senior lady was so active and delivering the lecture and the hands-on practical a whole day. Around 2 days, she has taken marathon sessions. And that was really touching to me. And today, for this second online program, she has agreed to deliver a talk on basically deep learning for detecting models and their applications. She was ex-director of IIIT Jabalpur. And I'm thankful, madam, and our stage is with you, and all participants are ready to start the presentation. Again, thankful to giving support to us, madam.
So first of all, let me thank Dr. Anil Kumar for giving me this opportunity. It is always so pleasant to interact with him. And he gave me this choice also of going there. Last time I was able to visit their wonderful institute. And it was really good because we found some of the very charming participants who were all the time active. So that was the reason I remained active for 5 hours a day. And incidentally, Dr. Anilji, today also it so happened because of the clashing, I have already delivered 4 hours of lecture, and this is the 5th. So 2 hours, 2 lectures I've already delivered. I told you that we were having some clash, but because of the time constraints and the topic constraints, we had to do it. So my dear participants, I hope you are all enjoying these sessions. In case of any questions that you have in your mind, please feel free in asking those questions. From time to time, because of the time limitation, I will be answering them. I don't know if there's a chat session here because this is my first experience. I'm putting my video off. For the
yes, ma'am. There will be there is chat box in the end. They will drop the questions, and between you can see that there is an icon coming, so you can see the questions raised.
Sure, sure. Thank you. So with this, let us begin with because we have to talk about deep learning. So let us begin with a brief introduction of what is intelligence and what is artificial intelligence for the sake of completeness of this topic. So if I look at what is intelligence, like as it is defined, ability to learn, understand, think, and act according to the given situation. That is what you call as intelligence. So what is artificial intelligence? Do we think that programs that behave like humans are AI, or programs that perform actions like human, computational systems that behave like intelligently, like, I mean, now you have more intelligent computational systems than humans. Talking about rational behavior, emotions, reactions to abnormal situations, these are some of the topics where AI experts are right now dealing with. So what kind of intelligence should be there to be called a completely artificially intelligent agent? I would like to quote here a couple of dictionary words and meanings of AI. And with this, I go ahead with the evolution of AI. If you look at the history of modern AI, although AI has been there for last several centuries, but the term AI, the modern AI, began to evolve when a very small group of scholars from a variety of fields started exploring the possibility of creating an artificial brain. And I would like to particularly mention these 3 great scholars of all time, Norbert Wiener, Alan Turing, John McCarthy, who were all instrumental in defining what AI is now. So in the Dartmouth conference in 1956, a group of scholars, all mathematicians, computer scientists, engineers, psychologists, and people from physics, they all gathered and thought of something which is now known as AI. So they, in that conference only, this term artificial intelligence was coined. And John McCarthy is one of the pioneers. Norbert Wiener was one of the pioneers in introducing, was the pioneer in introducing cybernetics. And Turing test is a test which Alan Turing introduced to define or specify if a machine can be called AI, artificially intelligent. So it is a simple test that if I ask randomly questions from a specific domain, and two people are answering, one is a human and the other is a machine, and if I'm unable to distinguish the answer comes from a man or a machine, then that is the probability of getting the answer from a man and of understanding that the answer is coming from a human or a machine is half, then that Turing test is passed. But then there are hardly many machines who have passed Turing test till now. So if I look at the AI system, all of you know that AI system has some ability, has an agent. That agent has some ability. Like, you know that humans have ability of walking, talking, thinking, many abilities, watching, hearing, touching. The same kind of abilities the artificial intelligence has. It may have some goals and preferences like humans have. For example, I may be having a goal from reaching from Jabalpur to Dehradun, and so I can have preferences like going by air, going by train, going by road. These are preferences, and then I do have prior knowledge of the environment. But this, the environment, I make the observations like this is rainy season, so I should not prefer going by road. So based on the past experience and the current observation of the environment, I take some actions. This is how agents in the environment work. These are artificially intelligent agents. So an agent can be an object, a hardware, a software that can gather information about its environment and take decision or actions based on that information. With this background, think about challenges that AI systems have. AI systems have many challenges. Like if you see, humans very quickly learn from the environment. There are challenges with the environment, like there can be incomplete information. Yesterday, suppose you are thinking about a robot path planning. Yesterday, in the path, there were no objects or obstacles. But today, suppose there is a change. Some tree has fallen. So this information can be sometimes incomplete. The environment can be dynamic, as I told you. One needs to process the sequence of percepts to estimate the missing details. Humans are very good at estimating the missing details. Like if there is a wall, there must be another house beyond this wall. All these things are easy for humans to understand, whereas it is very difficult for making artificially intelligent agents to think about anything, any situation like humans do. And it is hard for us to articulate the knowledge needed to build AI system. You see that it is said that we know better AI, we know better than artificial intelligence than the human intelligence, because we do not know in what way, in what aspects, in what dimensions human intelligence works in unison to solve a problem or to do anything. So it's very hard for us to articulate. So from here, when people started thinking about artificial intelligence, the concept of machine learning came. So what is learning? As per the Herbert Alexander Simon, who is a very well-known cognitive psychologist, he says that learning means what? change in the system that are adaptive. Means what? Suppose yesterday you were given some 10 numerical problems. You solve those numerical problems successfully, 4 of them, 6 of them you could not solve. Now, by learning with our past mistakes and the experience on those 10 problems, today if I am able to solve the same 6 problems with 6 of all those problems with 6 correct problems, and tomorrow maybe I can solve all the 10 problems correctly. If that happens, then I am learning. But you know that we tell our students, in case he doesn't learn well, by again and again telling the same thing, if he doesn't learn well, we say that you are not learning anything. So Bertrand Russell, a very famous philosopher and mathematician and computer scientist of all time, said, if asked why we believe the sun will rise tomorrow, we shall naturally answer, because it has always risen tomorrow. So what does that mean? Experiencing from the, like you have the past knowledge, it is the experience that is telling us what is it. So with this, if I look at the evolution of the artificial intelligence, you will find that AI started with the basic heuristic search algorithms, some very rigid type of algorithms, I would say, which is now known as good old-fashioned AI. It could not fulfill the expectations that humans had with the good old-fashioned AI, Go-Fi, in 1960s. Then the first winter came. During this winter time, the concept of expert system, knowledge engineering, all these came, and there was a second boom. But when I say boom, that means there was greater funding on the AI research and development, greater funding by the industry as well as governments. And then in spite of all this, there was not enough which was done by AI. And then came the second winter. During this period, the concept of machine learning emerged, this period. And since then, like although machine learning was doing good, but not as per the expectations of humans. You must be thinking, what expectation? In terms of natural language processing, in terms of image understanding or scene understanding. These are two very difficult tasks considered as very difficult tasks for computationally intelligent machines. But then in around 2006 to 2012, the concept of deep learning emerged. And this concept led to such significantly improved performance in the systems that you have now autonomous cars, autonomous weapons, so many things have emerged. And now we are looking for social excitement. You have social excitement also about various things that like autonomous cars, and you can see that the recommendation systems have become so good that the moment you click on buying a book from Amazon, it will immediately give you some 4 or 5 more recommendations. The moment you buy a cloth like a top, t-shirt, you will find that it will also give you many jeans and all those t-shirts also recommendation. Why this is happening? This is because deep learning has been deeply embedded in our daily life. But so if I look at why deep learning emerged so very well and why deep learning could supersede traditional machine learning systems, because if I look at the traditional machine learning systems, you must have seen that you need to craft features. Like given any machine learning problem, you will have to first of all pre-process the data. And during this, after the pre-processing, you also need to extract features from the data. If it is image, then you will have to maybe extract edges, some frequency, histogram, and all those things, some statistical features of the images, entropy, all these things, and then you will be submitting this to the machine learning algorithm, and then that will be giving the desired output that you want from the machine learning algorithm. So they are often over-specified and incomplete because we do not know what makes us understand an image or understand humans. Like humans, how do humans understand the complete image? That is something which is not very clear to us. So developing handcrafted features is a costly and complex job. Let me give you an example. Like suppose you tell a child that the green color is like this, like green leaf, green trees you will show, green some shirt you will show, green box you will show, and these greens will be of different variations. And then fourth time, if you will ask him or her, the child will immediately tell that this is green color. If you'll ask him, why do you think this is a green color? Even if you ask me, why do you think that this is a green color? It is difficult to answer, right? So although we do have some scientific knowledge of green color reflections, but in general, to a layman, if you ask, why do you think that this is green color or red color? It is difficult to answer, probably. So let us take this simple example of a image, and suppose you have to build an image captioning system. How do traditional machine learning systems work? They first will be handcrafting features like edges in this image, the texture information of the bird, texture, the color of the flower, and all those things. And finally, this will be sent to a trainable system having a machine learning algorithm. The output will be generated like a bird hiding in a flower, bunch of flower. So all this requires a good amount of handcrafted feature extraction methods. There is another problem with the traditional machine learning algorithms like support vector machines, naive-Bayes classifiers, traditional artificial neural networks, that with the increase in the dimension, their performance goes down. If you input an image of size 64 cross 64 to a neural network, it will do better. With the 500 samples of training samples, it will do better. Now, if you, instead of 64 cross 64, if you use 256 cross 256 with the same 500 samples, it may also do better, good. It will show good performance. But now think of 512 and 1024 cross 1024 images. You will find that the performance goes down. This is known as the curse of dimensionality. So with the dimension, if the number of samples remain the same, the prediction accuracy of a model initially goes up, but then suddenly goes down. This is known as the curse of dimensionality. Now, curse of dimensionality is also replaced with what is known as blessings of dimensionality. I will not go into details of this. So what could be the solutions? My dear friends, the solutions are deep learning models. You will ask me, what is a deep learning model? Deep learning models are nothing but convolutional neural networks or neural networks having a specific kind of training algorithms. So deep learning has emerged as a powerful solution to many problems that could not be handled efficiently by conventional machine learning algorithms. What kind of problems? Natural language processing like translation, machine translation, language modeling. All these problems could not be solved so efficiently by traditional machine learning algorithms. Medical diagnostics based on image understanding, signal analysis, gene expression analysis, traffic prediction and wireless network, anomaly detection and wireless ad hoc network, defense mechanism, all these were not possible using the traditional or the conventional methods. Well, my dear participants, I'm going a little fast because we have 1.5 hours in which I have to tell you two very important neural network architecture. But Please feel free in telling me if I'm going fast, okay? So what is deep learning? Deep learning, if I look at the big picture of AI, this AI here, deep learning is somewhere here. What does that mean? If I look at the conventional AI, where knowledge bases, heuristic search, all those were initially introduced, then came machine learning, the concept of machine learning, as I told you. For example, logistic regression, support vector machine, they were good classifiers. Regression, they were also good for regression. Those methods came up. Then people thought, no, this is not enough. We should also try to understand the representation of the data where from it is coming, so that we can understand better the characteristics of data and accordingly do our tasks. Those tasks would be classification or regression, for example. So representation learning concept came, and then came the concept of shallow autoencoder. What is an autoencoder? It is a neural network which extracts the feature of the data sample so that those features are able to reconstruct the original sample. That sample can be an image, that sample can be a signal, that sample can be a text sentence, or anything that you want to say. So what does it do? It learns to represent the input data sample. In this representation learning came the concept of deep learning. So deep learning, like deep multi-layer perceptron with large number of layers, are known as deep learning models. Okay, I hope this is clear to you. So deep learning, if you look at the traditional machine learning and the deep learning, the difference between the two, in traditional machine learning, you either need manual feature extraction or some algorithm to extract features before the samples are fed to the classifier or any, let's say, regression model. So suppose the problem is of binary classification, that given an image, can you find out whether there is a car in the image or not? For example, in autonomous driving, the vision system should be able to detect cars and other vehicles coming in the road. So the question is, can this neural network classify this? So first of all, you will be extracting features like it has some features like bonnet features and all those things. They will be extracted, and then that will be sent to the classifier, and then the output will come. Just see the down in this bottom. We have again the car, but this deep learning models automatically extract features. Feature extraction and classification, the job is done by the deep learning models. That means some initial layers do the task of representation learning so that they extract best features from the neural network, from the data samples. And then based on those best features, the final layers do the job. That job can be regression, that job can be classification. So in this case, it is a classification job. I hope this is clear to everybody, that the basic difference between the deep learning and the machine learning is that machine learning requires feature extraction separately before it is fed to the machine learning algorithm, whereas the deep learning doesn't require any pre-processing in terms of feature extraction, because it learns the representation of the data, and then based on the learned representation, it does the final task. So that is the basic difference between the machine learning, traditional machine learning, and the deep learning methods. So based on this, so what happens? Deep learning learns rich hierarchical representation. So what does that mean? Starting with say, suppose this is the image. So first it learns the low level features, that is color, edges. Combining those low level features, it goes to higher abstraction level, that is mid level features, where it combines those low level features to learn a bigger, like some other objects, or you can say some other constructs. Then from there, it also learns, by combining those, it learns the high level features. And these are then finally sent to the last layers or the trainable system, which gives the output. So idea is the same. The only thing is that now we don't bother about that part of feature extraction. Of course, data pre-processing is required in traditional machine learning as well as deep learning. By pre-processing means if it is an image data, then what will you do? You will be resizing the images to say one size 256 cross 256. Suppose the images are different sizes. You will also be changing the pixel values from 0 to 255 to 0 to 1. All these scaling, normalization, all this is already done, is also done in deep learning. But in deep learning, you simply feed that normalized raw data and it will automatically extract features, okay? So deep learning learns rich hierarchical representations automatically by extracting features at each level. Each level means initial hidden layers, the second hidden layers. I hope you have learned what is a neural network. Neural network you have read?
Yes, ma'am. Yes, ma'am. It's covered today only.
Yeah. Okay. So you know what is deep neural network. So now you can see with this deep learning, what impact deep learning has made on the general human life. Earlier, AI, we used to think that AI is the work of computer scientists, and that was within the small community of computer scientists only. But now, AI has spread its wings, and it has penetrated almost every field that touches human life. So you can see internet and cloud, from image classification to speech recognition to language translation, to medicine and biology, media and entertainment, autonomous vehicle. Just think about any application. Your mobile is a live example of so many applications involving deep learning. So what are deep learning ingredients? Deep learning ingredients are artificial neural networks as a learning machine, data. They are data hungry. Deep learning models are data hungry. Data, algorithms to train neural networks, and computing resources. It requires huge computing resources, but now we have those democratization of data, because earlier data was only available to small research communities. They have made publicly available many data of many domains. Then algorithms, very sophisticated algorithms have come up with for training neural networks. Then we have computational resources which are available free of cost, like Google Colaboratory, Kaggle. All these things are freely available. So you can, to some extent, it is any ordinary person like me, you can use deep learning models. So what kind of deep neural networks are there? One is the multi-layer perceptron that you have read. Then there are convolutional neural networks. Then there are recurrent neural networks and variants of these neural networks that are introduced by researchers for different tasks. So I seek your attention, please, now on understanding what is a convolutional neural network and what is the motivation behind it. So if I look at this traditional neural network or multi-layer perceptron, do you actually need all these edges, like the previous layer? All the neurons of previous layer are connected with all the neurons of the, so all the neurons of the current layer are connected with all the neurons of the previous layer. So these 9 neurons are connected with all the input dimensions. These 9 neurons are connected with all. Is it really required? Can some of these weights be shared? Like, suppose these neurons, some of them are working on, say, recognizing color intensities. So can it happen that the color intensities of this, it happens that some of them are learning, like this is independently learning to see the color intensity of green color, and this one is also learning. Is it possible that they share the parameters so that they learn together? Well, this was the idea with which convolutional neural network were introduced. So if I look at the image understanding problem, patterns to learn can be very small in the image as compared to the image size. For example, car detection in images. If I look at this, image is very huge, but the car is very small. So it's a small pattern that you have to learn. So a small pattern detector can be used in place of the entire weight parameter matrix, right? So I hope you know that here we use weight parameters and matrix. It is a, for example, it is 8-dimensional input layer and 9-dimensional in first hidden layer. Then it will be 9 cross 8 matrix. And here it will be 9 cross 9 weight matrix. All these weight matrices are learned. So what is the memory of the neural network? It is the weight and biases, which is the memory of the neural network. So instead of the entire neural network learning, why not let us take a small pattern detector? For example, and the pattern learning, like same pattern can be at different places in the neural in the image. So many same patterns. So can we slide the same pattern detector throughout the image to learn the patterns? That is also possible. When I say I'm sliding, that means I'm sharing the same parameters to learn the pattern. Okay. So convolutional neural networks use parameter sharing. That means neuron 1 and neuron 8 may be having the same parameters. And they use a small pattern detectors, they are called filters, to convolve over the entire image. Don't worry if you do not know what is convolution. These filters are learned. Remember, you learn the filters. I mean, you make the convolutional neural network learn the filters. While filters are learned, they are changing their weight parameters to learn the patterns. Some can be eye detector in face images. Some can be, say, in satellite images, it can be just aircraft or something that you have to detect. So these filters are learned through neural network training. Just like a hidden layer in neural network, convolution layers are used in CNNs. So convolution layers are what is you can call as hidden layers. To handle large size of image data, some pooling layers are also introduced. I will introduce this one by one. So let us first begin with convolution operation. Think about the left-hand side as your image data. You know that images are stored in terms of pixels, which are the picture cells, units of picture representation, pixels. So the intensities are represented in terms of values, real values. These are intensities, right? And suppose this is the filter that I want to, I want this filter to learn the patterns. So I will initially randomly choose values, like values here, 1, 0, -1, 2, 0, -2. These are the weights associated with the convolution operation, right? So this filter is the basically filter containing weights. Weights means how much weightage should be given to this, how much weightage should be given to this. This is what it learns. So let us say how the convolution operation is performed. So first I will be overlapping this over this. So what I do, I will be using say 5 multiplied by 1, this multiplied by this, plus 1 multiplied by 0, plus 7 multiplied by -1, plus 7 multiplied by 2 plus 2 multiplied by 0 plus 5 multiplied by minus 2 plus 5 multiplied by 1 plus 3 multiplied by 0 plus 5 multiplied by minus 1. Suppose the answer turns out to be 2. Like you just compute this and suppose the answer is 2. So by taking, can you see that this is a dot product? By taking 5, 1, 7, 7, 2, 5 and 5, 3, 5, right? I take this I have stretched as a flattened this and stretched this as a vector. Similarly here I stretch it as a vector -1, 0, -1, 2, 0, -2, 1, 0, -1, and I take the dot product of these two vectors, right? This is precisely what is this scalar product. And suppose this turns out to be 2, for example, right? So this 3 cross 3 area of image is convolved with this filter to give me one output 2, right? Okay. Next time what I'll do? I'll slide this filter by 1 pixel. This is known as a stride of 1, right? I will slide this pixel by filter by 1 pixel. So this is known as a stride of 1. And then I'll again do this 1 cross 1 plus 7 cross 0 and so on and so forth. Suppose the result again turns out to be some number. Let me call this number star. And then third time and then fourth time, right? So what will I'll get? Some values I will be getting 1, 2 values, third value, fourth value. Now I will do here. I will be again shifting it down by one stride of 1. And I will be getting another 4 values, right? Another 4 values and another 4 values. So I will be getting an output of size 4 by 4. You agree with that? I hope you agree with this. Have you understood that I'm overlapping the filter on this. I'm convolving this filter by taking the dot product with the image elements. And then I get an output. So the 6 cross 6 image is transformed to this 4 cross 4 output. Okay, this is what is known as a convolution operation. So suppose your image is say 32 cross 32 cross 3. Suppose what we do is that we take the filter with the same channel depth, because you are studying, you have joined a program organized by IIRS. So you may be knowing that the channels, number of channels depend on the number of sensors in a satellite. So there can be, say, for example, 14 channels, right? So accordingly, the size of the filter will also be changed, okay? So suppose the image is 32 cross 32 cross 5. I will be, what I will do, 3. On each channel of the image, I will be applying a 5 cross 5 filter. And this 3 and this 3, the filter will remain same. And the same filter will be applied here also and here also. Are you getting my point? The same filter will be applied 3 times on 3 channels. Okay. And then slide over the image, especially computing dot products, right? So you can see you will get one number. How you will ask me how one number, because there are 3 numbers I am getting. Those 3 numbers means 1 for red channel, you have calculated 1 number, 1 for green channel, 1 number, 1 for blue channel, 1 number. Then you add those 3 numbers to get 1 number, right? That is what happens. So you get finally 1 number for 1 position of the filter, right? For 1 position of the filter, you'll get 1 number. Okay. So what happens? The number of filters in a single convolutional layer are chosen by the user of the CNN. I just told you one convolution operation. Okay, that one convolution operator will use one filter, and that one filter will learn one pattern. But in an image, there can be n number of patterns. So what we can do, we can make use of n number of filters in one convolution layer. So what is a convolution layer? A convolution layer consists of an input volume, that is an image, a convolution operation with n number of filters, that is the convolution layer. And so the number of filters to be chosen in a single convolution layer are chosen by the user of the CNN, depends on the application of the data input type. Typically, a sizable number of filters are chosen, okay? For example, if the data is from satellite images, you will be using at least 64 filters in the beginning. Or if it is very complex data, you will be using 256 filters in the beginning, right? If it is a data of, say, some engineering drawing which have only black and white color, then you will be using merely 16 filters in the beginning. So what do you learn here? Filters are learned. Each filter learns to detect a small pattern in the image. And filter values are initially chosen randomly, like in the neural network, you randomly select the weight. So here I randomly select the filter values. Gradually, values are updated to learn a pattern. And how they are updated? Using the same stochastic gradient descent method that you used in the multi-layer perceptron. So activation maps are what? Activation map is once you get, say, output, say from 32 cross 32 image, 30 cross 3 image, for one position you got one value, and because you have convolved this over the entire image, you just saw that 6 cross 6 image becomes 4 cross 4, right? So similarly, 32 cross 32 will be mapped to a 28 cross 28 output. And so you will be getting a 28 cross 28 output. And that is what? That is nothing but weights multiplied by the image entries plus one bias vector, one bias. Because every, like, neurons may be having their own bias. Filters may be having their own bias. Why bias? Because humans also have their own bias. Like my bias would be towards lighter shades of clothes. Your bias can be for darker shades of clothes. My liking could be for going to, say, green and hilly areas. Or your bias could be go to Singapore or Dubai-like cities where you have a lot of architectural beauties. So biases are also there in the case of neurons. I hope I'm not confusing you, because today only you have learned neural networks, and today only you are studying convolutional neural networks. So it's just a sketchy, high level introduction that we are giving. So what I mean to say here is that you will be getting from a 6 cross 6 input, I got a 4 cross 4 output. Similarly, from a 32 cross 32 input with 3 channels, I get a 28 cross 28 output with only one channel. Why? Because all those 3 channel inputs that we got here, we have added. Like red color, we got one input, plus from green color channel, we got one input, plus blue color, we got one input. We added all these 3 inputs to give you this input. And for each position of the filter, I will be getting one input, one output. And so I will be getting 28 cross 28 outputs. On each of these 28 cross 28 entries, I will be applying an activation function. Activation functions are applied to introduce the concept of non-linearity. Otherwise, this will be simply dot product, a linear function. So how many activation maps will be generated? You use as many filters the same number of activation maps will be there. So suppose you use 6 filters. If you are using 6 filters, the output will be having 6 activation maps. Is that clear to you? The input dimension was, say, 32 cross 32 cross 3. You used 6 filters, so the output becomes 28 cross 28 cross 6. So output volume, that is the depth of the output, depends on the number of filters that you choose. Now, but remember that this 32 cross 32, next time it is coming 28 cross 28, then it may become, say, 23 cross 23, and ultimately with deep convolutional neural network, this size may go down to very small number, right? Very small size. To overcome this problem, zero padding is introduced. What is zero padding? We just pad in the image some zero numbers. It has 2 advantages. First of all, dimension reduction that was done by convolution operation is controlled. You can control it. The second thing is, which is more important, the corner pixels, agar aap dekhein, if you see, here it was what? I took convolution operation once, and when I slided it by a stride of 1, the contribution of this pixel was gone, right? But this pixel was contributing more. So the corner pixels were not having enough contribution. And therefore, to give edge and corner pixels better contribution, what we do is that we introduce this zero padding, and we start convolving from here. Then this. So you can see that this will have better contribution. That is what is zero padding. So now I come to input and output volumes, and I seek your kind attention, please, in understanding what is input and output volume. Suppose your input volume, that means the input image, is 64 cross 64 with 3 channels, right? I apply 10 filters, each of size 5 cross 5. Suppose I apply padding is equal to 1. That means, like here, padding means only one layer of 0, 0, 0 on all sides. Padding of 1 and a stride of 1. That is, I am sliding the pixel filter by 1. Okay. What will be the output volume? In fact, output volume can be determined using this formula. Suppose input image is of size n cross n. Filter is of size f cross f, and then the output volume can be obtained by this. So here in this case it is 64, n is equal to 64, right? So it will be 64 minus 5 cross 5 filters, so minus 5, plus p is equal to 1, suppose, so 2, divided by, suppose the stride is 1. So it will be the greatest integer. Suppose the stride comes 2 and this doesn't turn out to be an integer. So greatest integer contained in this plus 1. So here it will be 64 minus 5, that is 59 plus 2, that is 61 plus 1, that is 62 cross 62 will be the output volume. And if there are 10 filters, so output volume will be 62 cross 62 cross 10. Okay, this is the size of the output volume. Now the question is, how many parameters do you learn? You basically learn these 5 cross 5, that is 10 filters. So you will be learning parameters 5 cross 5 cross 10. 5 cross 5 cross 10 parameters. Plus, for each filter, you will be learning one bias parameter. So plus 10 bias parameter. So 25 into 10, that is 250, plus 10, that is 260. You will be learning 260 parameters. So this learnable parameters will be simply 260. If you compare this with the traditional neural networks, multi-layer perceptron, then the input dimension was of size 64 cross 64 cross 3. So even if the first hidden layer had only 100 pixels, So you would have learned so many 64 cross 64 cross 3 into 100 number of parameters. So it was huge computationally, huge problem. So that way, parameter sharing has worked well. Now, I told you that there's something called pooling layer. So when the image is large, one needs to compress the same for managing the input and output volume between different convolution layers. So subsampling the image does not lose image information, and pooling layers make the representation smaller. What is pooling? Pooling is like this. Sorry. Pooling is max pooling. It is nothing but subsampling. So take these 4 parameters, like these 4 values, and find out the maximum. This is 7. Take these 4, find out the maximum 0. Find out the maximum 5 and find out the maximum here 4. So I will be simply dropping the rest of the terms, and I will make this filter. From filter 1, this was the output that was coming, right? So I will be, this 4 cross 4 output will be further, goes down to 2 cross 2 output. Similarly, for filter 2, I will be applying the same operation. Okay. And average pooling is also applied. Nowadays, global average pooling is very much in use. So average pooling means I'll take the average of these 4, these 4, these 4, these 4. And if it is 13 by 4, it is equivalent to 3. That is how it does. Okay. Well, a generic. So now I seek your attention for how a generic CNN, convolutional neural network architecture, looks like. Suppose this is your input. First layer will be convolutional layer. What is that convolutional layer? 10 filters applied on input layer. Then I will be applying max pooling. For example, max pooling or average pooling, whatever. Then maybe again convolution, max pooling. As many times as you like, you will be applying here. There is another layer which is known as batch normalization layer. Batch normalization, which is done after a couple of convolution operations. Because sometimes, the data drifts from the center. So we put it back to the center if it is drifting, and normalize the data, right? So sometimes you will also find some BN layers here, right? And then batch normalize. So you will have as many layers you want. And then finally, whatever comes out, suppose the output comes out as 16 cross 16 cross 256, because I applied 256 convolutional, filters on the input. So finally I got this. This will be flattened. This is flattened. So flattened means this is transformed to one vector of shape, some shape which is 16 cross 16 cross 256 size cross 1. So this flattened layer is then sent to fully connected layer, which does the task of what? Classification or regression. In this case, it's a classification problem, cat or dog image. So these layers are doing what? These layers are doing representation learning. And what are these layers doing? These layers are doing the actual classification or the regression task. I hope this is clear to you. So there are several CNN architectures that have been introduced. This is one of the first very celebrated CNN architecture known as LXNet, now no longer in use because it's a very heavy model. It has huge number of parameters. VGG was introduced in 2014 in ImageNet large scale object detection challenge. It proved to be quite useful there. Then we had GoogleNet, which has 22 layers approximately, then 22 to 24 layers, I don't remember, but initial was 22 layers. Then came a very revolutionary kind of experiment done by Kaiming He Facebook researcher who introduced 152 layers. You will be thinking, what is new about it? Keep on adding layers. No, my dear friends, adding layers is not that easy because there is something called vanishing gradient problem. What happens in multi-layer perceptron or in any other neural network, convolutional neural network as well, when we back propagate the error, if the number of layers are very high, we use chain rule in computing the gradient of the error. So that chain rule involves multiplication by weight parameters. Weight parameters are lying between 0 and 1, for example. Then what happens? So many multiplication, as many layers, those many multiplications. And that leads to very small value or almost negligible value of the gradients or the partial derivatives of the weight parameters. So, I told you that weights are updated like this. A learning parameter alpha, W minus alpha del J by del W. Since this is vanished, this is gone. So W initially randomly selected W remains the same. There is no learning. And that was the problem that people were facing with deep neural networks initially. ResNet is one of the first such model with more than 100 layers, which was introduced by Kaming He in 2015. And wonderful thing about this neural network was that it was for the first time that in image object recognition in images, average human error from 1,000 classes of objects in 1.4 million images, the average human error was 5%. But this was able to make an error of less than 5%. So for the first time in the history of computer vision, a model was introduced that made an error that overperformed the human level of understanding of image. That is why this became very popular. Since 2014-15, you might have seen a lot of news about neural networks. Generative adversarial networks are the new era of neural networks, which were introduced in 2014 by Ian Goodfellow, but then they're finding enormous applications in different areas. We have attention-based convolutional neural networks, CNNs for specific tasks like the ones you might be interested in, remote sensing or aerial images and videos. Like these are some applications. These were my undergraduate students' object detection problems that I gave them. And these are also very small objects. Sometimes they create problem. So these are some of the examples where aircrafts can be detected and localized. You can locate them where exactly they are. So what is object classification, detection and segmentation? If I look at the classification localization problem, this is simply which class of object is present and where exactly is this. So you not only classify, but you also find out the bounding box. In object detection, there can be multiple classes of objects and we locate them where exactly they are by looking at the bounding box. By instance segmentation, I look at for each class, I find out what are the instances which are present. Like for the dog class, there are 2 instances which were present, this one and this one. And for cat class, I have 1 instance that is present. So this segmentation is also very important. Convolutional neural networks are used in all these 3 types of problems. Classification and localization, for example, I look at this, suppose there are 5 categories of objects in your data set and their corresponding labels, like 1, 2, 3, 4, 5 background, and you are interested in, you would like to train a convolutional neural network to classify the image and also locate the object, right? So the classification with localization requires classification task plus finding out or estimating the center height and width of the bounding box, right? So that is what is done. This is also found out. So basically, classification and localization or object detection problem is not only a classification problem, but a regression problem as well, right? So localization is a regression problem. Classification plus localization is done in object detection problem also. I would like to particularly mention here one very interesting method known as you only look once. So this is a state-of-the-art object detection method where what happens, you have an input image that is divided into grids. Only once the image is passed through the entire neural network, the earlier methods, which were not real-time methods like faster RCNN, although very accurate, but they were not, we were not able to apply them on for real-time applications like autonomous driving or autonomous catching the some activities by drone activities, like you saw Jammu Air Force, you saw that station was hit by drone. So is it possible to have real-time applications where you can capture an object? So what happens that we are divided into, say, S cross S grid at input. Each of this S cross S grid is then sent to the neural network, convolutional neural network, which classifies, which produces bounding box on one hand, plus the confidence score that this bounding box contains an object. First of all, it will estimate a bounding box, and then second, that the bounding, how confident I am, or the neural network is, that this bounding box contains an object, right? So that will be a confidence score, which is a probability of having an object in this bounding box. On the other hand, each grid element here is also sent to a class, like for a classification, where each grid will be looking at, will be trained, CNN will be trained on finding out whether each grid element, that cell, is containing an object, and if it is containing an object, of what class. Is it a background, or is it a dog class? Is it a cat class? Is it a cycle class? Then these two are combined together to produce finally the object detection, that means the box and their classes. So here you must have seen that this is the intermediate process. In this intermediate process, so many boxes are produced. And then finally, because of the confidence score, they are dropped. So initially, because I have to do quickly, right? When I'm doing quickly, I will be quickly collecting so many inputs, and then I will be eliminating them. That is what is done by you only look once algorithm presented by Redmond, a research scholar, and it was wonderful. Because of the lack of time, let me check if I can, and I am not very well versed with this GoToMeet. I don't know whether this presentation by Redmond and CDPR.
It's going fine, madam. It's going fine.
Okay. No, I wanted to show them a video, but I suggest them to study.
In the video, sound will be complicated. Sound will not come. Actually, it is complicated. Yeah, that is the thing.
No problem. I will skip this part. So it is a state-of-the-art object detection algorithm. There are other algorithms like M2DET, SSD, efficient DET. So many algorithms have been introduced. Well, I told you about what type of data, which is image. Now think of a video data.
You need to unlock your.
So you think about a video data, or speech data, or stock market data. So there are many applications that have sequential data, right? So are the general ANN or CNN good enough for such data? Answer is no. For this, we have sequence models or recurrent neural networks, which are very much used. So let us first understand what is a sequence data. Sequence data, for example, can be speech signal processing. The input can be one signal and the output can be language, written in a language. So speech signal processing deals with inputting of a voice signal or some speech signal, and the output will be something text written in a language, human readable language, right? The name entity recognition can be another example where we are looking for names in a text. Machine translation can be another model, like from English to Hindi. And activity recognition, where given a image or a video, you would like to see what is the activity going on. There are other kind of sequence data like sentiment classification. Wow, it is so nice. And so the output should be a number lying between 0 and 5. Music generation, a single number can lead to the encode, can decode to a string, a music sequence. Similarly, DNA sequence analysis. For these types of data, my dear friends, we have different input and output length requirement. There can be one-to-many, one-to-one, many-to-one, right? I just showed you some examples. Like one image, the caption, image caption can be many, like many words will be there. And then, wow, this is so nice. Then there can be just one number, like 0 to 5. There can be many to many, like name entity recognition. From this entire sentence, find out how many are names. So input and output will be the same. And there can be many to many with different numbers. Like, for example, Hindi to English translation. So input will be of length, say 5. The output will be of length 6. So these recurrent neural networks, which are a type of advanced RNN that involves directed cycles in the memory for sharing parameter across different parts of the network. Remember that we did not use in the neural networks or in the convolutional neural networks, the output of the current layer was not sent back to the previous layer, right? But here, in case of neural networks, it is shared. It can be shared. So it can access input and outputs of varying length, which is very important. It is designed to recognize sequential characteristics of data and use patterns to predict the next likely scenario. And the question is when to use RNN. Whenever there is a sequence of data and the temporal dynamics of that, that connects the data is more important than the spatial content of each individual frame, then use this. This is said by Lex Friedman, one of the scholars, very great scholars from Massachusetts Institute of Technology. So, my dear friends, recurrent neural networks look somewhat of this type. Here again, you have neurons, units, we call them units. You have sequential data like x1, x2, x3. Suppose this is the text sequence. With this, I will be pre-processing this text and will be tokenizing them, will be embedding them in a vector. And then I will be multiplying with the same weights. Remember, WAX, I'm multiplying. I have a vector of zeros initially. And with this also, I multiply the same weight. And each output I'm sending, you know, this output is a probability of something, right? Probability of the output vector. For example, for V, it can be hum. Go, it can be jao or ja rahe hain, something like that, right? So this is like you can see some difference in the structure, architecture, that each layer here, hidden layer, is independently acting and is also forwarding the output, some kind of output to the next layer, right? And this is what is recurrent neural network looks like, works like. So you can see that the forward and backward propagation are exactly the same, WAA, AT-1 plus WAX. So one coming here, coming from here, the another coming from here. This is coming from the previous layer. This is, for example, for this layer, X3, this is XT, A2, this is AT minus 1 multiplied by WAA plus WAX multiplied by X3 plus a bias vector, and then we apply a activation function. So this G1 is an activation function. YT hat is the output. It is generally the activation function can be a sigmoid or a softmax. That is what is done. So you must have seen that parameter sharing is here because everywhere you use the same parameter and the same parameter here, right? Okay, so parameter sharing throughout the input sequence. And remember that this sequence can be of different size, right? Okay. Forward propagation is to compute loss, and backward propagation to compute the gradient and then update the weight parameters. That is what is done. So you can see that from each, it is backward propagated, right? All right, so there can be different types of neural networks, like a vanilla neural network has only, say, 1-to-1, one input and one output. One-to-many for image caption kind of applications, for sentiment classification kind of application, many-to-one, and machine translation, it can be, say, many-to-many, and for name entity recognition, many-to-many, but with the same input and output. These types of recurrent neural network architectures are there in the literature. And forward and backward propagation, the loss function, if you see, is accumulated from each output, right? So loss function is added here. This is how loss is calculated. Well, a long short-term memory and gated recurrent neural network, gated recurring units are used here in this. Because why? Why? Because we were having vanishing gradient problems with this as well. What happened that, like, long sequences, I'm speaking for 1 hour, is a very long sequence of speech. So it has a very high dimensional data. It is a very high dimensional data. So the sequence will be long, even if it is, say, 30 words. So you can see that this will be 30, this will be having a depth of 30. If it is having a depth of 30, so vanishing gradient problem will occur. So to find out a solution for this, long short-term memory units, special architecture, because of the paucity of time, I cannot discuss the architecture. A long short-term memory and gated recurrent neural networks were, gated recurrent units were used instead of a vanilla neural network. So these are powerful models in all applications involving speech, natural language processing, language modeling, sentiment classification, stock market predictions, and any time series data if you have. Also combined with CNN for spatio-temporal data analysis, like for videos. And attention mechanism was introduced in the context of recurrent neural networks, which is applied with CNN also. They are producing very powerful, promising architectures for many real-life applications. I would like to give here one application from, say, video sequence, suppose from satellite images. You would like to see the segments of, say, smoke detection, right? So it's a simple application. One of my students, Shubhangi, is working on this. So you can see that smoke detection, it is there, right? So smoke detection, you know, is of very high importance because you might have seen many very sad news of this fire in jungles that has kept them, and that has devastating results. So miles and miles of jungles were all destroyed in US, in Australia, in India also. In many places, in many times it happens. So these are very important problems of smoke detection and segmentation. So this is a segmentation. These images are taken from NASA. And so these are some applications. References of this particular, not reference of the entire thing, sorry. Summary, you can say that machine learning is a branch of AI in which algorithms are developed that automatically learn the data patterns, right? That is very important. They learn the representation to take decisions. Decision can be classification, regression, localization, any kind of thing, right? So type of learning can be supervised, unsupervised, and reinforcement learning. You know that. You use these as these architectures as tools for supervised learning, unsupervised learning, or reinforcement learning. Remember that semi-supervised learning is used when the data is not fully labeled. And machine learning has led to several developments in practically all fields that touch human life. Game changer was deep learning. And CNNs and RNNs are promising architecture for learning models. Challenges with the deep learning are still there. First of all, this is data hungry. It's a lot, you need sometimes thousands and thousands of images. They also work like black box. No explanation of why they are making prediction. If they fail, why they would have failed. All these things are not known. So the new research directions in AI are on explainable AI or interpretable AI. With this, I wish to finally tell you that I happen to be the chief investigator of this Electronics and ICT Academy, which is a scheme of Ministry of Electronics and Information Technology of Government of India. We regularly organize online training and faculty development programs. And the upcoming programs generally we take 3 to 4 hours each day, working day, mostly as per the convenience of people. These are some of the upcoming programs which we are jointly running with all the other 6 academies established. There are 7 academies in the country. 3 are at IITs, 3 are at NITs, and 1 at IIITDM Jabalpur. And I hope many of you may be knowing that IIITDM Jabalpur is one of the institutes of national importance instituted by Ministry of Education. So those who are interested, I will also be running a course on deep learning in applications, as you can see here. From 23rd of August to 3rd of September, mostly in the evening time. All right, stay safe and healthy. Please follow all the protocols, even if you're vaccinated, because we have to make efforts that there's no third wave. Thanks. That's all from my side.
Very much thank you, ma'am, for giving wonderful talk, packaging everything in around 1.5 hour lecture. You started with AI, enlightening what it is, how different models coming under it, and then comparing conventional learning models, their limitations with deep learning, and then going inside the deep learning, enlightening all the participants about deep learning concepts. Then taken to CNN very nicely, using a board, conventional board, what I also love to use, pen on the screen. And it was really always to make all the students remain aware. And then you have taken to detection models, specifically the YOLO. There are so many others, but you've given an insight of the YOLO. And then RNN for sequential data, and the future prospects of AI where people can venture for their research activities. And thank you all, madam. I'm really thankful for the way you accept our support for giving your expertise in these programs. Now, there are a few questions in the chat box coming up. Madam, you can yourself
so
can see the chat box.
I am unable to see how to unshare. How to unshare. First of all, you gave me this tough task. And I'm happy that you passed me, that I could cover all the things in 1.5
But
hours.
you have done so nicely that
Thank you,
AI
sir.
was bringing all the things in the time. Really,
Thank you.
we are thankful for that. There are 3 or 4 questions only. Madam, you
So
can
how
see in the
to,
chat box.
Chat box. Let me. I saw some thing
On the top
I
side,
don't know.
on the top side, if you see right hand side, the second button is there. On the right hand side top. Or okay.
Yeah, now I can see. Now I can see.
Yeah.
So there are some questions like how many times it is harder to process real-time application or live situation compared to stationary ones? How many times? See, whenever you have real-time applications, so real-time applications they will always pose challenge when you run a model which is not built for, which is not designed for real-time applications, because real-time applications have a lot of dynamic environment changes. Changes are very, they are very rapidly changing. In that case, it is not possible. So I will not be able to tell you how many times, but think of any applications like autonomous driving is one such application, or say real-time detection of heartbeats, or pacemaker. Pacemaker is, it's a very simple device which is there in the heart of a person, and it makes the pace. But think of, suppose this pacemaker is not malfunctioning. So you will be applying a real-time AI-based sensor that will detect whether the pacemaker is properly functioning or not. So that there you need real time, right? So that is one application. So one needs to have real-time applications many a times. Shraddha ji is asking if you do face recognition and if you use algorithm for that, so filters for already there in the algorithm, or we do have to define filters? No, you have to learn filters, not define. Those filters will be randomly, first of all, selected, and then you can use well-known architectures like Siamese network or networks with triplet loss. Siamese network is a well-known network which is very well established to be a good architecture for face detection problem. So you will have to learn the weights. The third is, how can we differentiate the smoke and cloud from the satellite imaging? Very interesting question. And I think Dr. Anil Kumar is more competent to answer. But for automatic detection, it is one of the real challenges of distinguishing between the cloud and the smoke because of the environmental conditions. So if you wish to work on this, please start working from today. This is a very challenging problem. And Ram Nivas Giri is asking, what are main differences between 2D convolution and 3D convolution? So 2D convolution is the one I told you, and the 3D convolution, whenever you have, like, for example, the temporal data, which video, you can use a 3D convolution there, right? So you have a time as also as the third dimension. So there we use 3D convolution.
I hope there is no more questions.
Okay. So I thank you once again, and all the participants. Thank you so much.